Welcome. In this video, we are exploring how some of your favorite guitar effects like vibrato, flanger, chorus, and doubler are all powered by a simple yet powerful idea: modulation using variable delay lines. Let's decode the sound science behind that legendary tone. Let's start with the flanger effect. It's that swooshing jet engine kind of sound. It's created by mixing the original guitar signal with a slightly delayed version of itself, where the delay is modulated sinusoidally. As the delay varies, the comb filter notches move up and down the spectrum, creating that hypnotic sweeping effect. Let's listen to it. So first without the effect on, and then with the effect on. Beautiful. Next is chorus effect, a lush shimmering tone that makes it sound like multiple guitars are playing in unison. It's achieved by mixing a delayed signal where the delay is slightly longer than a flanger and modulated more slowly. The result? A rich, detuned feel that adds width and depth to your sound. Let's listen to it. Wonderful. Now on to vibrato. Unlike tremolo, which modulates volume, vibrato modulates pitch by varying delay time without mixing in the original signal. It's a pure pitch modulation effect, and when used subtly, it adds emotional depth and expressiveness to solos. Pay attention to the foot of the guitarist. A wobbly underwater kind of sound. At the heart of all these effects is a variable delay line. It's a simple idea. Take your input signal, delay it, and control how much delay you apply over time. And here where the magic begins. By tweaking that delay dynamically, you shape your tone into something truly expressive. Now how do we implement this? Well, in digital systems, the delay M is typically an integer. We access discrete pass samples from a buffer. Here, xn is the input, this is a buffer, and the output is yn. And this arrow represents variable size of this buffer, which is represented by m. In analog domain, these delays are implemented using special ICs called bucket brigade devices, and these are no longer manufactured, but still you can find few of them online. In both the systems vary the size of the delay buffer, either in steps or continuously, to achieve modulation. In this plot, you see two diagrams. On top is, in blue, there is sinusoidal input to the system, which is xn, and red is the delayed output of the buffer. And as you can see, the phases are varying, the phase shift between the input and output is varying depending on this modulating signal. So when this modulating signal is at its peak, the delay is large, and when this modulating signal is at its trough, both the input and output, they coincide, meaning zero phase shift. So this is what is a LFO, or a modulating signal, which decides how much phase shift is going to be imparted. In analog domain, this is a continuous signal depicted by this black line, and in digital domain or in software, it is an integer system which is in steps, as shown by this magenta line. More about it when we implement it in Python. Now once we have a phase shifted output, we mix both the input and output signals in some proportion, and what it gives rise to is this green wave. So here you see, because of phase differences, because of phase opposition between the input and output, which is in the background, the phases are getting cancelled, and the net output is that here the signal loses its amplitude. And wherever the input and output phases are not very highly shifted, or they are matching, the output is increasing in amplitude. So at some places we have amplitude which goes attenuated, and in some places we have amplitude which rises up. And this is what is a phase modulated mixed signal. And in frequency domain, the net impact is that there are notches in the spectrum which are moving up and down, creating that jet swooshing sound. This is the spectrum of that mixed signal, and as you can see, on the bottom axis, on the horizontal axis, we have frequency starting from 0 Hz going up to 21 kHz, and on the y-axis, we have power spectral density. And what we see is that there are notches at frequency 1 kHz, 3 kHz, 5 kHz, 7 kHz, so on and so forth, basically all odd harmonics. We have these notches, and these notches are because of attenuation of signal in these zones. All right, theory is great, but let's see it in action. In the next part of this tutorial, we'll dive into a Python demo that simulates a variable delay line in real time. We will visualize how the signals get delayed and how notches form in the spectrum and how delay modulation translates to sound. In this section, we'll build the variable delay line. I have used some libraries here, so let's get started. So let's start the sampling parameters first. Let's say my sampling frequency is, let's say it is 1000 hertz. 1000 samples per second. Let my frequency of the input signal be 10 hertz. The duration of the signal is 1 second. And so how many samples do I have in 1 second? Very simple. It is sampling frequency, that is number of samples per second, into time, that is duration. So this will be a floating point number, so I have to convert it into an integer to have integer number of samples. So this will be my number of samples, and let me create the time axis. So my time is linearly spaced numbers starting from 0 seconds to the duration of the signal. And how many such numbers do I need? I need n numbers, and my endpoint is false. Okay, so this is my time axis. Let me create the signal now. That is xn. My input xn. Input to the variable delay line. Input to the delay line is signal in, and it's a sinusoid, so it is a sine signal into pi into frequency. Remember, frequency is 10 hertz into the time axis. So as you can see, this is what is my signal. Let me do a quick plotting here to see whether we are on track or not. So time versus my signal in, and you can see that this is the xn input to the delay line. Now let me create a modulating signal so that it varies the length of the delay line or the size of the delay line. So that modulating signal is again modulating signal or LFO or whatever that you want to call it. So that signal itself will have a frequency, let's say modulation frequency of 2 hertz. And what is the maximum delay that this delay line will impart? So that, let's say, is 50 milliseconds. Now this is in millisecond. We want to know the entire length of the delay line in terms of samples. Basically, we're trying to find out the M as shown in the presentation. That will define the size of the delay line. So we have to convert this into samples, and that will be max delay samples. So it will be nothing but the total delay that we want to implement, that is delay ms multiplied by the sampling frequency. And since this delay ms has to be converted back into seconds because the sampling rate is in samples per second, so I have to divide it by 1000. And this will result in a floating point number, but our samples have to be integer. Our m is integer, so I have to convert it back into integer. And if you want to have a look at what this number is for this particular delay, we can just print it out. So here, for a sampling frequency of 1000 hertz, to implement a delay of 50 milliseconds, our delay line should have a buffer size of 50, which means this is what is the M, as mentioned earlier in the presentation. Now this M needs to vary. So as of now, we have just gone to the maximum delay, but this delay has to vary. And once the delay varies, this size also varies. The buffer size or the delay line size also varies. So how do we implement that? So basically that delay variation is sinusoidal in nature. So what we're going to do is, let's define delay line analog. So that will be nothing but I will start with my maximum delay samples, and I'll go to the center of it, right? So this is what is the axis around which the modulating signal will oscillate, and I'm going to then define the modulating signal around this axis. So that will be sine 2 np pi into modulation frequency, that is 2 hertz, into time. Wonderful. So let's see how this delay line looks. So we have an error here. One bracket is missing here. Okay, so here is our 2 Hz signal. The signal duration, the total duration is 1 second. That's what we have defined here. Duration is 1 second, and modulation frequency is 2 Hz. So these are 2 cycles of that modulating delay. Now these are, the y-axis is in number of samples. So if you remember, our max delay is 50 samples, and we start exactly at the center of it so that we don't get into negative samples. There's nothing called negative sample. It can at best be, at the minimum it can be 0. So that's the reason we start in half. We start from 25 samples, it goes up to 50 samples, and then it comes back to 0 samples. That means no delay, and that's how this entire delay line is varying over a period of 1 second. That is throughout the duration of the signal. So this is fine. We don't need this. So in fact, I want to show you something here. This is a very smooth function because it's an analog line. But as we know that our m is an integer, and we cannot entertain floating point numbers. So let me just make a delay line which is discrete in number. That means samples are discrete, they cannot be continuous. Let's call it digital delay line. And what it entails is that these floating point numbers should get converted into integers. Great. So let me plot this digital delay line also. If you remember, I said that analog delay line is created by special ICs called BBDs, bucket brigade devices. They are no longer available. Now we are implementing it in software, so we have to have integer values of m, not floating point. So that's the reason we have to do this. We have to convert this entire thing into integer, and let's plot it. So as you can see, the blue line was the analog delay, which is continuous in nature, but since we are implementing it in software, and m can only have integer values, so you can see these quantizations here. These are discrete sample locations, and as you can see, the delay line size is varying from when it starts at 0 seconds. It has 25. It is 25 samples wide. Then it keeps on increasing, and here it reaches 50 samples, which is the maximum delay. And then the size of the delay line starts to drop, and at this point, it is having 0 samples. That means whatever is the input, without any delay, it is passed on as the output. So that's how this entire size of the delay line is going to get varied. So now let's implement the delay line itself. This is just the modulating signal, which is changing the number of samples. So first let me just put a placeholder for the output signal. That means yn, the output of the delay line. So that's signal, let's say the signal out, and that is nothing but all zeros. And how many number of them? As many as the length of the input signal, which is n samples. So here I will store my output signal, and let's now implement this variable delay line. For that, I will go through each and every sample of the input. That means for n in range length of the input signal, I can also say capital N here. Now, what is the delay at the start of the loop? The start of the loop, the delay is the first sample, and then the next iteration it will be the next sample, and in the next iteration it will be the next sample until it goes and touches 50. So I define that as d, the instantaneous size of the delay line, and that is nothing but delay line digital and the nth element of it. So n starts from 0, the first element of that digital delay line, which is going to be sample 25th. That means 25 millisecond delay it will start from, is the first initialization of this number. And now we have to wait for this entire delay line to fill up. That means 25 samples must fill up before the first sample at the output becomes available. So we need to put a condition to check this, otherwise our delay line won't work. So if n is greater than this delay line size, at this point it is 25 at the start of the loop. So if n is greater than 25, this is what it's saying. This condition makes sure that the entire delay line has got filled up with the input signal, and now the output is available in the next clock. So if the entire delay line has got filled up, what to do? That means now whatever that I'm receiving out of this delay line is my output, the first element of that output, the first item in the list, and which is nothing but the input signal which has become available after a delay of d seconds. That means if n is, so this if statement, the code inside this if statement will get executed only when n is greater than 25. So when it is, this is 25, whatever is the first element of the signal, that becomes the output. That means it has been delayed by 25 millisecond in the first iteration. Otherwise, the delay line has not filled up only. So if the delay line has not filled up, then the output remains 0. So the output remains, signal out remains 0. That's it. So this is how we are going to implement the delay line. And once this signal out is completely available to us, we are going to create another signal. We call it signal mixed. Now we have two signals. XN is the original signal, and XN as in signal in is the original signal, and signal out is the phase shifted version of it. So we are going to take signal out, mix it with signal in, and in what proportion? Let's say we are going to take an average of it. So this is what is my mixed signal. That means 50% of my signal out will get mixed with 50% of my signal in. And rest is all the plotting code. So I've written some plotting code. In the first plot, we are going to generate the plot for the input signal, then for the output signal, and then for the signal which has got mixed in 50% proportion, that is out plus in. And we'll generate a second plot. We are plotting our analog delay line and our digital delay line. So let me just run this code now and hope that everything is working fine. Great. So this is working fine. And okay, let me just explain these plots one by one. So I'm disabling my out signal and my mixed signal and just plotting my input. So as you can see, on the x-axis we have time going from 0 to 1 second. So our duration of signal was 1 second. And on the y-axis we have the amplitude, and we have a sine wave having 10 cycles here. So if you remember, this is exactly what we had programmed here. Our duration of the signal was 1 second, our frequency was 10 Hertz, and it is a sine input. So this is what we have achieved here. Now let me just plot the output of the delay line. Let me rerun the code. So now this green signal, once this, if you see here, initially the output of the delay line is 0 because it's filling up, and once the delay line gets completely filled up, then the output is available. And as you can see, the output is phase shifted. Here the distance is the phase shift between the input and output is very large, and here it is very low. And in the bottom plot, I have plotted the modulating signal, which is changing the length of the delay line. So on the x-axis again I have time, which is from 0 to 1 second, and on the y-axis I have the size of the delay line in terms of samples. This is basically the variable m, as was shown in the presentation. So this m is varying from 25, it goes up to 50, and then it comes down, it goes to 0. So this m is varying, and since the size of the delay line, or the buffer size of the delay line, is changing continuously, so the delay will change continuously. And since the delay is changing continuously, once you see that once the delay line has reached its maximum size, which is 50 samples, I am having the maximum phase shift here. And when the delay line reaches its absolutely minimum size, which is 0, which means there is no delay, input is being passed out as output. So here actually you can see when the delay line has got 0 size, my input and output are perfectly overlapping. So this is the example of how a delay line can implement phase shift using time delay. And the whole concept is that the size of the buffer of the delay line is continuously varied using a sinusoidal modulating signal.